Greetings everybody, and today we're going to be coming up with a generalized solution to the mixture problem, which is one of those questions that you often see when you study differential equations. So what exactly is the mixture problem? Well, you have some tank over here, and you have some fluid coming in and some fluid coming out. And the idea is there's going to be some kind of concentrate that's mixed inside of this fluid. So for example, maybe we have some water inside of this tank with some kinds of concentration of salt. And let's say we're pumping pure water in, and then we're draining out whatever's in the tank. So as you can see, over time, the concentration of salt will decrease because we're pumping in pure water. And other examples include, let's say you have some kinds of concentration of sugar and you want to increase the concentration of sugar, then you pump some kind of sugary solution in while taking some out to keep the volume constant. Stuff like that. You can model all those scenarios with differential equations. So what are the variables we're going to be using, or the parameters? Well, this tank is initially going to have some kinds of initial volume that I'm going to call V0, and it's going to have some kinds of amount of concentrate. Maybe it's 5 kilograms of salt that's initially dissolved in here. So usually we denote the amount of concentrate with X, but in this video we're going to be considering something else called C0, which is the initial concentration. It's a little bit easier to think about it that way because we're going to be considering the concentration when we look at the inflow of fluid. So these are going to be the main two things that we're going to be looking at: the initial volume and the initial concentration. And as for the inflow of fluid, there's two parameters we need to consider, namely how fast the fluid is flowing in, which I'm going to call Rn for the rate of inflow, and also the concentration of the concentrate that's flowing in, which I'm going to call Cn. So maybe the fluid flowing in is coming in at 5 liters per minute, and as for the concentration, maybe there's 3 grams of sugar for every liter that's coming in. So those are the two things we can think about when we're considering the inflow. And as for the outflow of fluid, all we really need to do is consider the rate of the outflow, so R out. Alright, so from all of this we can start constructing some differential equations. I'm going to be starting off by looking at the volume. So volume, we know a couple things about how the volume changes. So if we take a look at dV dt, and V is going to be the measure of how much fluid is in the tank. I guess I'll just write it over here. V is going to be the volume of fluid in the tank at any given time. So dV dt, well, the change in volume is really the change in the volume that's coming in minus the change in volume that's going out. So if we're pumping in liquid at a rate of 3 liters per minute and we're taking out liquid at a rate of 1 liter per minute, then the net change per minute will be 2 liters per minute. So that's kind of what we have over here. And what we know what dV in dt is, that's exactly how fast the liquid is flowing in, which is Rn. So we can say this is equal to Rn, and as for the rate at which the volume is changing that's going out, that's exactly R out. So Rn minus R out. And this difference in rates over here, I'm just going to be defining that as delta R, so difference in rates. So we have dV dt is equal to delta R. We can solve this differential equation by integrating both sides with respect to t, and we get that V is equal to antiderivative of delta R, which is just a constant, is delta R t plus some arbitrary constant. Let's call it C. And what exactly is C? Well, we know some stuff about the initial conditions of the volume. We know that at time 0, initially, we have a volume of V0, which means if we plug t equals 0 in, our V should be equal to V0. So we can deduce from there that our constant should be V0, because if we plug 0 into here, then V is equal to V0. Alright, so this perfectly models how much volume is in the tank at any given time, but the more interesting is modeling how much of that concentrate, which is X, that's in the tank at any given time. So now we're going to be taking a look at dx dt, because we can figure out some stuff about how the concentrate is changing. So just like the volume, this is equal to dx in dt minus dx out dt by the same kind of intuition. And dx in, we can actually figure that out. We can figure out how much stuff is flowing into the tank based off of these two parameters over here, which is R in and C in. And I forgot to mention one important relationship, but the amount of concentrate is equal to the volume times the concentration. So X equals V times C. So for example, if we have 5 liters and the concentration is 3 kilograms for every liter, then altogether we have a total of 15 kilograms inside of that volume. So we know R in is exactly dV in over dt, as we have over here. So let's multiply both sides of this equation by C in, which is the concentration. So C in and C in. And notice that this is exactly X in. And notice over here we have V in times C in, the volume times the concentration, which is the total amount of stuff that's inside of that volume. So this is exactly dx in over dt. So as you can see, dx in over dt is exactly the concentration in times the rate of inflow that's going in. So we can make that replacement. This is exactly C in times R in. And then as for dx out dt, well, again, just like over here, we're going to have some kind of concentration and we're going to have some kind of rate. And this is the stuff that's going out. So the rate is going to be the rate of the outflow of the fluid. And the tricky part is, what exactly is this C? Well, the problem is this C is dependent on what's inside of the tank, because the stuff inside of the tank is the stuff that's flowing out. And the concentration is always changing. So if we refer back to this formula, how do we figure out the concentration? Well, notice that C is exactly X divided by V. It's the amount of stuff divided by the volume that it's in. So we can make that replacement. This is exactly X over V. But notice, what exactly is V? V is exactly this expression, which is delta RT plus a V naught. So we have now R out divided by delta R times T plus a V naught times X. And this is exactly dx over dt. Alright, so notice we've constructed this nice differential equation, and now our goal is to solve this thing. And notice this is a first order linear differential equation because we have our differential and we have a singular x over here times some kind of function of t. And there's also one important thing I need to point out over here. Notice that in order for this to be a first order linear differential equation, we need the condition that delta R is non-zero, because if this thing is zero, so if the rate of inflow matches with the rate of outflow, which means delta R is zero, that means we don't have a first order linear differential equation, and we can just solve this thing using separation of variables or something like that. So we're going to assume now that delta R is not equal to zero, and then after we find the solution, the generalized solution to this thing, we're going to consider this case as well. Right, so I've just written out all the stuff we just found up here, and now our goal is to solve this differential equation. What I want to do first is to move this term onto the other side. So now we have dx over dt plus R out over delta RT plus V naught times X is equal to this constant C in times R in. And now we need to multiply everything by the integrating factor. So now we have dx dt, and then we have an x, and over here, this is some function of t. And the integrating factor, which is rho, is exactly e to the integral of this function, which is R out over delta RT plus V naught, and we integrate this with respect to t. So our integrating factor rho is equal to e, and now integrating this, that's not too bad. We have the R out constant that can jump out of the integral, and integrating this, that's just going to give us the natural log of delta RT plus V naught, but we also have to divide by the derivative of the inside, which happens to be delta R. So we have R out divided by delta R. And notice I didn't include absolute values over here because I'm going to assume that everything in here is positive. Because notice this inside over here, that's exactly V, as we said before, and it doesn't really make sense if V is negative. So we're going to assume it's positive, so we don't need the absolute value sign. So now we know that rho is equal to, now notice we have a natural log and a base e, so this inside of natural log can come down to the base, so delta RT plus V naught, and we still have this power up here, which is R out over delta R. Alright, so we've figured out our integrating factor. Let's multiply the whole entire differential equation by the integrating factor. And we're going to get that rho dx dt plus rho R out over delta RT plus V naught times X. And I'm going to put this in parentheses, is equal to rho times a Cn Rn. And notice we can now use the kind of the reverse product rule on this thing, because we have a uv dash and then a vu dash. This whole thing over here is the derivative of our rho. So now this thing on the left hand side, that's exactly the derivative with respects to t of, we're going to have rho times x, but rho is this thing, so I'm going to write that down. So delta rt plus v naught to the r out over delta r times x, and this is equal to rho times Cn times Rn. So we're going to have Cn Rn times our rho, which happens to be exactly this stuff over here. So delta Rt plus V naught raised to the R out over delta R. Alright, now we have another kind of differential equation. We have a derivative of something is equal to something else. So in order to get rid of this derivative, let's integrate both sides with respect to t. So now this left-hand side is just going to be turning into this function we have in here, which is a delta rt plus a v naught raised to the r out over delta r times x, and that's equal to the integral of this thing, which is Cn Rn. Those are just constants, and integrating this isn't really too bad. It's just a bit of reverse power rule, so we add 1 to the exponent and we divide by the new power. So let's divide by the new power first. So 1 over, we're going to have r out divided by delta r plus 1. And then over here we're going to have delta rt plus v naught raised to the r out divided by delta r plus 1. So I hope you guys can see where all this is coming from. Adding 1 to the exponent and dividing by that new exponent. And we also have to divide by the derivative of the inside, because this is a linear function in here. So derivative of the inside is delta r, so let's divide by that as well. So 1 over delta r. Notice we're going to have some cancellations going on in here. So on the right, we're going to have Cn Rn, and distributing this delta r into this denominator, we're just going to be left with r out, and then plus delta r, like so. But notice r out plus delta r, what exactly is that? R out plus delta r, but delta r is r in minus r out. So these are going to cancel out, leaving us with r in. So on the denominator, we're just going to have r in. So 1 over r in. But notice this and that will cancel out as well. And then we still have this delta rt plus v naught. And then over here, we can do some more simplifications, because notice we can replace delta r with r in minus r out. And let's try to combine these two terms together. So 1 is exactly r in minus r out divided by r in minus r out. And notice r out and minus r out will cancel each other out. And we're left with r in divided by, well, this thing over here is delta r. So we're left with r in divided by delta r. Alright, great. So now we have this left-hand side expression is equal to Cn times this junk over here. And in fact, I forgot the constant of integration over here after we integrated this thing, so that's pretty important. Let's add that in before we forget. And I should probably call that something like K, so we don't get mixed up with the concentration C. So now we are left with delta RT plus a V naught raised to the R out over delta R times X is equal to Cn delta RT plus V naught to the power of R in over delta R plus some constant K. And now let's try to solve for this constant K. Because initially, if we have some initial volume and some initial concentration, then we're also going to have some kind of initial mass. So we're going to let T be equal to 0 and X be equal to X naught. But remember, X is exactly V times C. So that's V naught times C naught. So letting T be equal to 0 in here, we're left with V0 to the R out divided by delta R. And then x will turn into v naught times c naught. So we have another v naught, so let's add 1 to the exponent. Then we have a c naught, and this is equal to cn. And letting t be equal to 0 in here, we're going to be left with v naught raised to the Rn over delta r, and then plus k. And now if we take a look up here, I want to make a couple modifications to this, because remember 1 is exactly delta r over delta r, but what is delta r? It's r in minus r out. And as you can see, r out will cancel out with the minus r out, leaving us with r in divided by delta r. So we have a v0 r in divided by delta r times c0, and then let's subtract this term on both sides. So we have a minus v0 r in over delta r times cn, and then this is equal to k. But notice we can do a bit of factoring over here, because we have a common factor of v naught to the Rn over delta r. So if we factor that out, we're going to get that factor and then c naught minus cn, like so. And that's exactly our k constant. So now if we plug this back into our equation that we had, we're going to get delta rt plus a v naught, r out over delta r times x is exactly cn delta rt plus a v naught, r in over delta r, and then plus k, which is a v0 to the r in over delta r times c naught minus cn. And now all that's left for us to do is divide both sides by this factor, and we're left with x of t is equal to cn, and then notice we have the same base over here, so we're going to take this exponent and subtract this exponent. But notice that's going to give us r in minus r out, all divided by delta r, which is the same thing as delta r over delta r, which is 1. So you're going to get delta r times t plus v naught, and then plus v naught to the Rn over delta r times c0 minus cn. And then remember, we're dividing both sides by this factor. So let's multiply by this factor, but introduce a negative in the exponent. So we're going to have delta rt plus a v naught, and then to the minus r out divided by delta r. And this right here is basically the generalized solution to the amount of concentrate in the tank at any given point. So it's a pretty complicated formula, but what do you expect from such a generalized result? So if you can identify all 5 of these, or I guess 6 of these values in here, and plug it into this formula, then you get an equation that models the amount of concentrate that's inside of this tank at any given time. Alright, so we found the solution to when delta R is not equal to 0, so when the inflow rate is different from the outflow rate. And now let's consider the case for when delta R is equal to 0. So that's when you're pumping in fluid at the same rate that you're taking out fluid. So if delta R is equal to 0, well, that means that R in is equal to R out. And let's just replace this with a single parameter, capital R, like so. So notice R in and R out are going to be the same thing. So we're just going to replace those with just an R. So dx dt is now equal to, and we can also factor out that R as well. So we're going to have R, and then on the inside, we're going to have a Cn minus x over, and delta R will be 0, which just leaves us with V0, like so. Okay, and I want to combine these two terms together to kind of bring it together as one fraction. So let's multiply the top and the bottom by V0, and we still have our Cn, and then we're subtracting this x. And everything's being divided through by V0, but we can also take that V0 out to the very front, and we're going to have R divided by V0. Okay, and notice we have dx dt as being some function of x. We can use something like separation of variables if we want to. Let's bring this factor onto the other side, and we're going to get dx divided by v0 times cn minus x is equal to r divided by v0, and then we can bring the dt over, like so. And now it's just a matter of integrating both sides, and that's pretty easy to do. On the left-hand side, if we integrate this, we're going to get the natural log function. So we're going to get natural log absolute value of v0 cn minus x, but we also have to divided by the inside derivative, which happens to be just this -1. So we have to make sure we have a negative over here. And on the right hand side, we're just integrating this with respect to t, and we're just going to get this constant times t. So we're going to get r divided by v0 times t, and let's bring this negative onto the other side actually. Makes more sense that way. And then we also have some arbitrary constant c added on to the very end. Okay, now our goal is to isolate this x. Let's start by exponentiating both sides. So if we have e to the left hand side, e and the natural log will cancel each other out, leaving us with just the argument inside, so v0 times cn minus x, and then this is equal to e to the minus r divided by v0 times t, and then we also have e to the c as well, using some exponential properties, but that's just going to give us some random constant a multiplied out the very front. And notice over here, this absolute value, just make sure that the whole left hand side is positive, but the inside of the absolute value could be either positive or negative. So we have to kind of consider both cases for that. So we want to get rid of the absolute values. And this inside could be positive or negative, so plus or minus a, but this a, but again, that's just another constant. So we can just leave it like that if we want to. And now let's try to figure out our initial conditions. So we know that at time t equals 0, x will be equal to x naught, but x naught is just, well, v naught times c naught, so volume times concentration. So let's plug t equals 0 into here and see what we get. So if t is equal to 0, we have e to the 0, which is just 1. So when t equals 0, we just have a on the right hand side. And then as for the left hand side, this x will turn into v naught times c naught. So a is equal to v naught cn over here, and then minus this x, which we want it to be v naught c naught. So minus v naught c naught. And as you can see, we can factor out v naught. So a is equal to v naught, and then cn minus c0, like so. Okay, now let's plug everything in. We're going to get now that v naught times cn minus x, this whole left hand side, is equal to a, but we know a is equal to v naught times cn minus c0, and we have e to the minus r divided by v naught times t. And now we just have to isolate this x. That's quite easy to do. Let's add x on both sides and then subtract this whole entire right hand side expression from the left hand side as well. And if we do that, we're going to get x is equal to v naught times cn, so v naught times cn, and then we're going to subtract off this whole entire right hand side, so minus v0, and then cn minus c0, e to the minus r over v0 times t. And you can choose to factor out a v naught here as well if you want to, but I'm just going to leave that. So that's our final expression for x of t, and this is for when delta r is equal to 0. And if delta r is equal to 0, then we're just going to take r in being equal to r out, and we're going to let both of those be equal to that one parameter r that we have inside of this solution. So there we go, those are our two solutions to x of t, and of course both of those have their corresponding solutions to v as well, which is the amount of volume that's inside of this tank at any given time. But both of these equations will give you the amount of mass or the amount of concentrate that's inside of this tank at any given time. You just have to be able to identify all these parameters, plug it into these equations, and then you can use it however you want to. And I guess it's an interesting observation as well. When the difference in rates is equal to 0, we have an exponential function, but when they are different, we don't quite have an exponential. We have growth that kind of follows t to the p, where p is some power, so kind of like a polynomial growth maybe. So that's quite an interesting observation right there. But yeah, that's pretty much all I have for you guys in this video today. I hope you guys enjoyed it, and until next time, hope you guys have a wonderful day, and I'll see everyone later. Bye bye.